それではですね、2つ目のセッションを始めさせていただきたいと思います。次のセッションは、GPU Acceleration of CAE Simulation というタイトルで、NVIDIA の CAE 担当のシニアアライアンス&マーケティングマネージャー、ブッシャン・デサムより、トークさせていただきます。Bhushan, please start your presentation.
Konnichiwa. Good afternoon. And as for the introduction, I manage NVIDIA's partnership with major ISVs such as ANSYS, and also work closely with companies like Fluent in offering GPU accelerated simulations. And I'm very excited to talk about this topic today and also help you explain how you can shorten the product development life cycles and effectively manage the product development process using GPU accelerated simulations. So here is the agenda for this 1 hour session. I'm going to briefly explain how GPUs are revolutionizing enterprise computing, and then highlight some of the challenges in product development that are being faced by many companies. Also, quickly emphasize the role of simulation in addressing those challenges, and then explain how NVIDIA GPUs accelerate CAE applications, and then move to particular applications in CFD, mainly ANSYS Fluent and Fluid Dyna solutions, and then discuss structural mechanics applications such as ANSYS Mechanical, Abaqus, and MSC Nastran, and then briefly touch upon computational electromagnetics applications such as ANSYS HFSS, and then present our offerings in accelerating the CAE applications, and then conclude with a value proposition for GPU simulations. So NVIDIA GPUs have been increasingly used in enterprise computing. Many of you already know our Quadro solution to accelerate graphics applications such as CAD and rendering. But the same graphics technology that does really good things with graphics can now be used to accelerate computing, which is basically offered through our Tesla product line. And our grid solution is becoming a choice for enterprises to secure data and to improve the workflow, especially when they have to move large amounts of data from data centers and HPC clusters to do the visualization. So you can think of grid as a remote graphics solution in the context of CAE, where you can keep the data on the HPC cluster, but display the graphics on thin clients, such as a low-end workstation or even on tablets that doesn't have a lot of computing power, graphics power locally. So as I mentioned, our Tesla is an accelerated computing product line, and the Teslas are nowadays being used by the most greenest supercomputers in the world to accelerate scientific and technical computing. And because of the unique characteristics it delivers, a lot of major ISVs such as ANSYS and Simulia are also leveraging GPUs to accelerate the engineering simulations for better design workflows. So as I mentioned, the world's top 10 energy-efficient supercomputers use NVIDIA GPUs, according to the latest, the Green 500 list, including Tsubame at Tokyo Institute of Technology. So in this globally competitive environment, these are some of the business challenges that product development companies such as automotive and other manufacturing companies are facing today. Delivering a quality product is becoming a must criteria. I mean, you cannot fail by delivering a low quality product. So, and then that also what's important is you want to do it faster than your competitors. So going to market quickly with a quality product is also important. And the products are becoming more and more complex. So how do you manage this complexity is another challenge the businesses are facing. But if you actually go back 20 years ago, you can see that simulation is being widely used to address all three of these in improving the product quality, getting faster to the market, and managing the product complexity. So it is adding a lot of value to the product development companies, such as automotive companies. And not only the simulation is being widely used, but the way simulation is being used is also going through a drastic change. So again, if you see it in the past, simulation is mainly used to explore the design space that we know very well. So what I mean is, if you have a design space, you are trying to design a product, and if you think each of these points are a design, you use simulation to reduce the number of experiments you need to conduct to deliver a product. So a lot of companies who are leveraging simulation to just bring their costs down with experiments. So they want to actually get insight from simulation in product development. But if you pass and if you see how simulation is being used in today in automotive OEMs, they're actually using for product innovation. What I meant is, with simulation now, you can go beyond the design space that you know before and completely pick a design concept purely with simulation without heavily relying on experiments. These experiments are costly, and sometimes you cannot actually conduct these experiments. So this is a way of actually doing product innovation just through simulations, or it is well known in the simulation community as simulation-driven product innovation. But to achieve this virtual prototyping or simulation-driven product development, you need to do a lot of simulations. But the biggest challenge is computing capacity. So this is a survey done by one of the major ISVs, ANSYS, over 1,800 customers. And the data that they gathered is showing almost 1/3 of the customers limit the model size because they're worried that it's going to take too long to complete the simulation. So the time to simulation is very important, and to keep it more tractable, or to keep it in content, so they're trying to limit the model size. So one problem with that is you're compromising quality of your simulation. If you compromise quality of simulation, the simulation is not being, the simulation won't be much helpful to do product innovation. And similarly, more than half of the people limit their model size on some of them. So again, the same challenge. But only 9% or a minority of the people have all resources. They have enough computing power. They are the people who don't need enough computing power. But the majority of the CFD or structural mechanics users are saying, we need more computing power. Of course, CPUs can deliver the computing power. But if you actually compare the latest generation CPU versus an NVIDIA GPU, you can see what NVIDIA GPUs offer. So both the floating point capacity and the memory bandwidth are important for CAE applications. And see how the CPUs are tracking. So this is the Sandy Bridge and how it's making improvements in terms of delivering floating point operations. When you look at GPUs, the GPUs are actually, they're delivering more and more very quickly as we make improvements in our architectures. Similarly, on memory bandwidth too. So you are having almost 6 to 8x kind of improvement over a CPU in terms of computing power. So how can you leverage this computing power to accelerate CAE applications? So this is just a very basic description of GPU computing, which most of you are already familiar with. So the idea is to use GPU as an accelerator, because the major ISV codes are written on CPUs for years and years. ANSYS has been around for more than 25 years, almost 30 years. And they have millions of lines of code running today on CPUs. So, but if you can move some of that code to GPUs and use GPU as an accelerator, that can actually deliver benefits to CAE users. And also, most of the time, especially when it comes to ISVs, the GPU acceleration is user transparent. You don't need to know CUDA. You don't have to actually code in programming, such as CUDA or OpenACC. The ISVs take care of it for you. All you have to do is specify, how many GPUs you want to use, and that should take care of the details, in the background. And so this is how it works. You start your job on a CPU as before, and the CPU does some operations and communicate with the GPU when it's necessary, and then the CPU delivers a solution. So, which is pretty straightforward. And what's happening in the background when it comes to a CAE application? How are GPUs accelerating the CAE application? So if you take any simulation such as CFD, for example, if you are using an implicit solver, so the kind of steps there are, you have a mesh that you pre-process it, and then you do discretization, and then there is a linear solver portion, and then the solution update portion. So out of that, you can quickly move the linear solver portion to GPU and accelerate that either using CUDA or using libraries. Once again, this will be done by ISVs, not you as an end user. And still, you use CPU for other operations, for example, discretization, solution updates. So by combining these two, by actually leveraging both CPUs and GPUs, now you can accelerate your application by 2 to 4x. So that means what used to take a day, you can now do in 6 to 12 hours. Okay, so let's now dive into some more details of particular applications, and CFD being the first one. And here is a landscape for GPU accelerated applications in CFD. So ANSYS Fluent is, as you know, is one of the most widely used codes. We accelerate that. And we also accelerate Altair AccuSolve, Autodesk Moldflow. This is a particle-based code, which is CPFD Barracuda. And we are also working very closely with Fluid Dyna in Germany in offering a solution for OpenFOAM, which I also am going to describe in detail in a bit. And then Fluid Dyna also have other code called UltraFluidX. It's shown as Albertra, but it's been recently renamed as UltraFluidX, which is a lattice Boltzmann solver. And the LB solvers are highly suitable for parallelization on GPUs. This is where you can expect almost 10x kind of speedups. and they are making a lot of progress in accelerating the lattice-Boltzmann solutions. And there are other applications that are GPU accelerated today. So now I'm going to describe the GPU acceleration features that were introduced in 15.0 back in December of 2013. So that was our first major release in Fluent, where we have accelerated the heart of the CFD engine. And this is how the GPU acceleration in Fluent works. So if you take a Fluent simulation, you can basically divide that into two parts. The one part is the algebraic multigrid portion, which is the linear solver that I've been talking about, which typically goes to GPUs. And the non-AMG portion, which includes the matrix assembly or the discretization or the solution update. So anything that is outside the linear solver can be grouped into non-AMG. And Fluent offers two kinds of solvers under pressure-based option. One is a coupled solver, the another one is a segregated solver. So the coupled solver typically spends a lot of time in the AMG. So you would see typically 60 to 70% of the time goes to AMG when you switch on your coupled solver. And that makes the rest is only 30 to 40%. So when you have a GPU, this AMG portion goes into GPU, and then it communicates with the CPU for the rest of the code, and then together it accelerates your application. Because the AMG portion is nearly 60 to 70%, you can get very good speedups in coupled solver. But when it comes to the segregated solver, it only goes to 30 to 40% of the time goes to GPU. So you don't see much benefit of really using a segregated solver with GPUs in version 15 at least. So we are actually working closely with ANSYS in coming up with a way of actually accelerating segregated solver. So what can you expect? What can you expect in ANSYS Fluent? What kind of speedups can you expect? So this chart basically explains what is that linear solver fraction that you are sending it to GPU. For example, if you are sending 70% of your time is spent on AMG, if you are sending this to GPU, and if the AMG algorithm on GPU gets accelerated, let's say by 3.5x, you can get a 2x in Fluent speedup. That means what used to take in 2 hours now only takes 1 hour. But the speedup also depends on what kind of scale up you are getting on your AMG. If the AMG is only delivering 2.5x, then you only see 1.7 or 1.8x. So this is you got to keep in mind that whatever the acceleration that you get in AMG won't directly translate to the total solution time, because linear solver is only a part of the problem. In addition to bringing the AMG acceleration features in Fluent, ANSYS completely revised their licensing policy. And the way it works is basically each GPU socket, the whole socket, is treated as a single CPU core when it comes to licensing. So that means with the same number of licenses, you can now do more number of simulations to either reduce your product development lifecycle or to explore more design points. And in addition to that particular change, now any ANSYS HPC product can unlock GPUs. So before 15, it only used to be something called HPC packs. But now you can use GPUs with HPC core licenses, HPC packs, HPC enterprise. So any HPC pack should unlock GPUs. So the way it works in 15 is each HPC per core license unlocks one GPU. Or when it comes to HPC pack, in 14.5, each HPC pack only used to unlock one GPU, but in 15, each HPC pack can unlock almost 4 GPUs, the first one. The second one can unlock 16 GPUs out of 32 processes. So just by taking the same number of licenses, as I mentioned, you could actually get more simulations done with the existing resources with GPUs. And let's take a look at some of the performance in ANSYS 15 when you put your simulation on GPUs. So this is a water jacket model. So this is a thermal management simulation that is typically done in the automotive industry. And what I'm showing here is the left side chart shows the speedups in AMG. On the right-hand side shows the speedups in the total solution time, which is most interesting to you. And when we ran this problem on 8 CPU cores, which are Intel Xeon E5-2680, which is Sandy Bridge, and to do 20 time steps in this unsteady simulation, it was taking 4,500 seconds in the AMG solver. But by adding 2 K40s to this simulation, now it dropped all the way to 775 seconds. That is a 5.9x speed up in AMG. But since AMG is only 50 to 60% of the total simulation time, when it comes to the total solution time, this 5.96 is now delivering about 2.5x, because I believe this simulation has 55% of the time in linear solver. So this is how a typical problem works when it comes to acceleration. But the real acceleration depends on your own problem, because each problem will have a different linear solver fraction. And the rule of thumb is the larger the linear solver fraction is, or the larger the percentage of the AMG is, the better speedups you can get. So what about the value proposition? I've been talking about we can accelerate your simulation, but to accelerate your simulations, you have to invest in GPUs. If you invest on GPUs, what is it going to return to you? So this is an example where we ran an aerodynamic case. So this is a Formula One standard case that is owned by ANSYS. And this problem has 144 million cells. And when we ran this on 160 CPU cores, it was taking 25 seconds per iteration. And when we added 32 K40 GPUs to this particular simulation, now we could do 12 seconds per iteration. So the speedups here are almost 2.1x. And let's now talk about the value proposition or the cost and benefit analysis for your investment if you choose GPUs. And the way you need to do that is you have to consider the system cost in doing this kind of analysis. What I meant by system cost is your hardware cost, at least your license cost, because licensing is a key component of total solution cost. So if I take that for ANSYS, and this one was run on 8 nodes, and if I take the hardware costs on a Fluent license on 160 HPC licenses, and that amount I am actually showing here as 100% on the cost. Now, adding 32 GPUs and 32 additional licenses would cost me 55% more. But look at the benefit. This 100% is delivering 100% productivity that is equivalent from the 25 seconds per iteration. However, the incremental benefit that is coming from GPUs is almost 110%, because if you take the speed up of 2.1x, 1x is coming from CPU, and 1.1x is coming from GPU. So that is 110% more productivity from your simulation. So when you take the incremental cost versus incremental benefit, that means I'm putting 55% more investment, but I'm getting 110% more. So that is 2x additional productivity from HPC licenses and GPUs. So that's how you should evaluate your value proposition. Also, how do GPUs scale on large problems? So this is a question that we keep getting from our customers. So the way we did this study is there are two variables there. One is to keep the same CPU to GPU ratio and then change the number of CPUs and GPUs. And the other way is change the CPU to GPU ratio itself. So if you take the first set, which is run on 120 CPU cores and 24 K40s, we're getting about 1.9x. I'm keeping the same CPU to GPU ratio of 5 here in the middle chart, but now I am actually increasing my CPU count and my GPU count. By increasing that, now I'm getting 2.1x. So my performance improved with more GPUs and more CPU cores. But here, I'm actually now reducing the number of GPUs per CPU. And you can actually see now the performance is 1.8x. But the performance is actually around the 2x for a reasonable CPU to GPU ratio. So that's something that you should note. Just to highlight a customer story on ANSYS Fluent, so this is one of our early customer success stories that we did with PSI. So PSI is an engineering service provider to aerospace industry with major customers such as Rolls-Royce, GE. And the way actually their business depends on is to really deliver highly excellent technical solutions to their customers. And what they have always do is they always take the latest and greatest, both in software and hardware. So whenever ANSYS releases a new software, they immediately embrace that, and along with any hardware innovations. So they also took NVIDIA GPUs, and they noticed almost a 43% reduction in Fluent solution time on one Intel CPU socket versus NVIDIA K40. And the impact that they're receiving is they could actually deliver the simulations on time, but doing this, without compromising the quality. So this highlights what GPUs typically bring to a product development company or an engineering services company. Some ANSYS Fluent resources that you can access, or we have an ANSYS solution page that you can access from nvidia.com/ANSYS. And we also recently published a user guide on how to use GPUs in Fluent 15 that you can access from ANSYS website through their resource library. And I have also delivered recently a webinar on how to speed up ANSYS 15, which describes the solution even in more detail than what I discussed today. So this one is recorded, and you can actually go and access that from ANSYS if you are interested. So now let's switch gears from ANSYS Fluent solution to FluidDynam. FluidDynam is an innovative German company that is developing products such as Culises and Aerofluidics to bring GPU acceleration to OpenFOAM and also in general and other solvers. And I'm going to first discuss about Culises. So as I already mentioned before, any CFD calculation involves you have a pre-processing step, a discretization, a linear solve, and post-processing step. So the linear solver portion of this calculation is handled by a library called Culises. Culises is a state-of-the-art library that is built upon AMGX libraries developed by NVIDIA that are optimized for GPUs. And the Culises offers you multi-GPU support on multiple nodes, so you can actually run your calculations on several machines, and each machine have more than one GPU, and both in single precision and double precision mode. It offers both the Krylov subspace methods such as conjugate gradient method and also multi-grid methods. And right now it has a flexible interface, but right now the implementation is for OpenFOAM, but it is not limited to OpenFOAM. And any code can be accelerated by integrating with Culises with minor changes. So how does Culises perform on a typical automotive OEM problem? So this is an actional aerodynamics problem. And on the CPU side, it's optimized both on CPU and GPU so that you have a fair comparison. So on CPU side, the calculations are run with geometrical algebraic multigrid. And on GPUs, it is actually being handled by AMG preconditioned conjugate gradient method. And these results are over 200 iterations. And the study is done on two different measures. One has 18 million cells, and the other one has 62 million cells. And we have used different number of CPUs and GPUs. But the key observation that you should make is, what kind of speedups are we getting on the linear solver, and what kind of speedups are we getting on the total simulation? So when we pair up 8 CPU cores with 1 GPU, the linear solver is delivering almost 3.8x, whereas the total simulation time is 1.6x. So you can easily see that the linear solver is half of the total simulation. So 50% of the time is spent on linear solver, but the rest of the 50% is spent on other areas. And when we added one more GPU to the 8 cores, now the performance went from 3.8 to 5.5, and the total simulations also improved. The performance of total simulation also improved from 1.6 to 1.7. So similarly, it shows the performance on high number of CPU count and also high number of GPUs. But the amount of acceleration you can get by just accelerating the linear solver is limited, especially in the context of OpenFOAM. Because in OpenFOAM, when you use an equivalent of a segregated solver option in Fluent, that is where you solve each equation separately, you solve pressure, you solve U, V, W, and turbulence equations, the amount of linear solvers portion actually is lower compared to a coupled solution where you combine some of these equations and solve it simultaneously. So because of that, the overall speedups that you can get in OpenFOAM is limited just by accelerating the linear solver. That's exactly what this is showing. So if you take only 30 to 50% of the linear solve time, and if you are accelerating the AMG by 2.5, your speedups are not going to be more than 1.5x. But if you want to get 2x, if you want to get more than 2x, you need to do more than just using Culises. So this is where I believe Fluid Dyna is in a very unique position where they're also accelerating the matrix assembly portion of the CFD on GPUs. And this is how it works. Instead of just sending the linear solver to GPUs using Culises, now they're also using they're using GPUs for handling discretization. Just to give you a sample of how it improves the performance, so this is the aerofluidics benchmark on an airfoil flow problem. And so this is the CPU profile. So the CPU, let's say it takes 100 seconds, and out of that, 75 seconds is spent in linear solver, and 25% is outside the linear solver. Just by accelerating with Culises, you can get 1.35x on this portion. And by adding the aerofluidics, you can now get 2.23x by just moving the matrix assembly to GPUs. But in addition to that, you can also get better performance from Culises because the equations are now being assembled on GPUs. And now the GPUs, when you solve on GPUs, you don't have additional communication. So overall, it actually improves the acceleration. And the product planning for aerofluidics is, right now, the implementation is only steady state, laminar flow on single GPU. But sometime in the third quarter or later, Fluidana will have a turbulent implementation, at least the K omega and the Spiralat-Almaraz models. And also, there will be a multi-GPU and multi-node support. Later, that would be extended to doing more unsteady turbulence, such as LES, larger dice simulations, or DES, and then making it more generic. So initially, it's going to be single-phase flows, typical to aerodynamics, for example. But down the line, in a couple of years, it should become a generic solver to do everything on GPUs. And just to summarize this portion, Culises takes a hybrid approach where you use both CPUs and GPUs to solve your problem, but the acceleration is limited. So, but aerofluidics is an implementation where you also move the portion outside the linear solver to GPUs. As a result, you can actually expect speedups are 2x or more. So I'm going to switch gears and now cover the structural mechanics applications. Again, this is a comprehensive list of applications that we accelerate using GPUs. And I'm going to discuss ANSYS Mechanical first. And the way it works in ANSYS Mechanical is like in ANSYS Fluent, as I described, we send the linear solver portion to GPUs. Here, we send the matrix factorization to GPUs because this is typically, like in some problems, it takes a lot of time just to do the matrix factorization. And this task is highly parallelizable, and it suits better for GPUs, and it's also easy to implement for ISVs. And what kind of speedups can you get when you send the matrix factorization in a direct sparse solver problems? So this is a standard ANSYS mechanical benchmark, which is a V14SP5 turbine geometry. It has 2.1 million degrees of freedom, only has solid elements. It's a static nonlinear analysis done in distributed mode. As I mentioned, it's a direct sparse solver. And when you do the simulation on just two CPU cores, you could actually complete 108 jobs in a day. But when you added just one Tesla K40 to the simulation, now you could do 410 jobs per day. So that is almost a 3.8x improvement in productivity. So this is with the base license, but if you have HPC pack, which unlocks 8 CPU cores, and you could now do 307 jobs with 8 CPU cores. But when you added a Tesla K40 with the same HPC pack without additional licenses, now you could do 757 jobs per day. That is a 2.5x improvement in productivity. So this looks like a very good acceleration for this particular application. And what about the value proposition? I showed you the acceleration. So I'm picking another model, V14SP6 model, to explain the value proposition. So this was, when you run it on a base license, you could do 59 jobs per day. And when you added a Tesla K20, you have 2.8x more productivity from your system. When you compare the cost, if the base license and the workstation cost 100%, just adding a Tesla K20 and one HPC license only cost you 25%. But this 25% is delivering almost 180% additional productivity. So you get almost a 7x additional productivity for the money that you are spending on GPUs and just one HPC license. So same analysis, same problem, but done with HPC pack, where you are getting 1.5x productivity on your simulations, but that is now converting to almost 50%, that 50% acceleration is now converting into 4x in additional productivity. So when you consider GPUs, what you need to look at is, it's not just the acceleration, but what is the value of the acceleration, both in terms of your investment and also in other factors such as, time to speed to market and, other factors. So this is a key takeaway. So another success story, say PSI Inc. They have been using GPUs for almost, since the release of ANSYS Mechanical almost 3 years ago. And this is showing ANSYS 14.5.7. And this problem has 5.8 million degrees of freedom, ran on 8 CPU cores with 64 gigabytes of RAM. And when using NVIDIA C2075, which is a previous generation GPU, they could actually cut their simulation time by half. So they could get 2x more productivity just by adding a GPU to the simulation. So some of the resources on ANSYS Mechanical, again, our ANSYS solution page has more details, including I highly recommend reading this article if you are using ANSYS Mechanical and if you are considering GPUs. This is published on ANSYS Advantage magazine in 2013. And also the webinar describes the ANSYS Mechanical solution in detail. So I'm going to now take another structural mechanics application, which is now this time Simula Abaqus, and show how you can accelerate those simulations with GPUs. So the GPU acceleration feature has been in Abaqus since 2011, but they've been actually doing more and more improvements. So the first when it was released, it was only supported on a single GPU, but later extended to multiple GPUs in 2012, and then extended to unsymmetric solver, unsymmetric solver from Symmetric in 2013, including our latest generation card support, which is the Kepler series. And so this is Abaqus 6.14 is slated for release in this month. And that is going to bring several important features. And one of that is you can now handle many problems with less memory. So the new implementation uses memory very wisely. And also there is a new option, which is the DMP split, which dramatically improves the performance of GPUs in Abaqus. And also the AMS eigensolver is also ported onto GPUs in 6.14. So this is a benchmark from Rolls-Royce, which you might have heard of this company. And when the simulation is done on 8 cores on one DMP process, it is taking 5.1 hours. And when we added K20X GPUs, the simulation time is cut by 3.3x, which is a dramatic improvement. And it's only taking 1.5 hours. And the same simulation, when we did this on 2 DMP processes, CPU is taking 3 hours, GPU is taking 1 hour, so that's a 3x improvement in performance. So this shows the typical speedups in Abaqus in a problem like this. Again, coming to value proposition, we have a 2.4x acceleration on 20 cores with 2 K20X GPUs. When you look at the solution cost to incremental spending, so you are only spending 15% more in terms of GPUs, but that is delivering almost 140% additional productivity. So when you normalize it, you are getting almost 9x additional productivity per dollar spent on GPUs, which is compelling. So also, I just want to highlight the performance with this new DMP split feature. So the DMP split feature is already implemented on CPUs, and it has been available for a long time. But in 6.14, it's going to be also available for GPUs. And this performance is run on over many cases. I'm not explicitly going to describe each case, but if you see, these are all ordered by the factorization requirements. But if you see the first bar here, that was without the DMP split feature, but the second green bar is showing with the DMP split feature. So now there is more. This is not comparing CPU to GPU. This is comparing GPU in 6.13 to GPU in 6.14. Relatively, there is high performance here. So the performance went from 1.3x to 1.9x just with this feature. And this is consistently across all models that we ran. We have about 5 models, benchmark models, that we noticed the same trend. So this is, again, a customer case, but we can't reveal the name of the customer. But this is relevant to automotive industry. And again, this study was done on 2 nodes, 3 nodes, and 4 nodes, and how you can see how the CPU is scaling. And when you add a GPU, you can also see how the GPUs are also scaling. So this shows how you can reduce your simulation times for a model like 11 million degrees of freedom. So this model is pretty big. So I'm going to briefly touch upon MSC Nastran is another application in structural mechanics that we accelerate, and we've been successful. And in MSC, the direct equation solver is GPU accelerated. The factorization is sent to GPUs, and it can handle very large fronts. And also, it impacts several solutions such as static stress analysis, model analysis, and model frequency response studies. And it also supports multi-GPUs in Nastran, and it supports Tesla Kepler series, such as K20, K20X, K40, K6000. And you need a separate license feature to really unlock unlimited GPU sockets. This is a timeline, of MSC Nastran's implementation of GPU. So it was introduced back in 2012, version 2012, and then they've been making several improvements over the last couple of years. Coming to performance, I'm showing 3 benchmarks here: hollow sphere, piston, turbine blade. And for the hollow sphere, we have about 2.65x improvement in productivity. And for the piston case, it's 1.7x. For the turbine blade, it's 1.7x. And for piston case, it's 1.68x improvement in performance against a CPU socket. And most of these performance studies are done by adding a GPU to a CPU socket. So that translates to almost 30 to 70% of time savings in your workflow. So very briefly, computational electromagnetics applications. Again, this is the whole list of applications that we accelerate. Includes, for example, ANSYS, HFSS, ANSYS NextSim, CST microwave, and other applications. And by the way, all of these accelerated applications are listed on our website under GPU accelerated application guide that you can download it. And it describes all of these for different areas, not just in CAE. So just briefly, on ANSYS HFSS supports transient analysis in 15. And the benchmarks are actually done over a range of problems. And the average speed up of 2.4x over a single CPU socket is observed in these benchmarks. and the maximum speed up of almost 5.2 against a Tesla K20X when you paired up with a CPU socket. So which again shows pretty good performance on ANSYS HFSS. So coming to our hardware solutions, these are some of the GPU cards that we highly recommend for CAE simulations. So our Kepler series, which is so far the latest series in GPUs for computing. The Tesla K20 and K20X has 5 to 6 gigabyte of memory based on which card you select. These are ideal for structural mechanics simulations unless you are dealing with a problem bigger than 5 million degrees of freedom. And that's when you should consider K40, which has more memory. It has 12 gigabytes of memory on it. This particular card is highly suitable for CFD because CFD is very memory intensive and you need a lot of memory. And our Quadro K6000 is almost equivalent to our K40. It has the same memory, nearly same flops, but it can also handle graphics. So you could do both graphics and computing on the same card on your workstation. And we also offer a MAXIMUS solution for workstations. A MAXIMUS solution is nothing but it has two GPUs. One is a Quadro GPU to handle the CAD operations and pre and post processing, such as graphics applications. But at the same time, it also has a Tesla to handle the computing in structural mechanics or CFD or electromagnetics. The beauty of this is it's managed by a single driver, and it's being offered by many OEMs such as HP, Dell, and Lenovo. And by just taking this optimized system, you can accelerate your CAE applications. So just to conclude, what are the benefits of GPU accelerated simulations? So if I can conclude in just one sentence, you could do more simulations in the same amount of time or same number of simulations in less amount of time. What that translates to is, it translates to some value. The value in improving product quality by doing more design points in a given period of time, or you can also do these simulations faster and cut your time into nearly half so that you can bring the products to market quickly, or even in handling complex simulations where the mesh sizes can be doubled, or even you can turn advanced physics models to get more accurate physics out of your simulations. So these are some of the benefits and value in investing in GPUs. I think that's it. That's the end of the presentation. And thank you for your time. And
Thank you, Bhushan. ここで、ご質問があればお受けしたいと思いますが。
If a model is composed of a small number of nonlinear elements and large number of linear elements, then there would be a load balancing would be an important issue. Do you have a good idea for load balancing from the viewpoint of hardware developer?
So are you talking about a structural mechanics application?
Yes, yes.
So whether it's a linear or non-linear analysis, it will have a solver time. Okay, for example, if the solver time is 60% or 70%, or the factorization time I would call when you are using a direct sparse solver. As long as that is high, you should benefit from GPUs. It doesn't matter whether it's a linear analysis or a non-linear analysis. But we can't really particularly address the load balancing. We cannot look from the load balancing point of view because we don't know the kind of applications that you run. But our general recommendation is the higher the matrix factorization, the better you can leverage GPUs. If that matrix factorization is very low, probably you don't get much benefit because you don't have much control on the load balancing at all. I mean, if the factorization is only 10%, it goes to GPUs. If it is 90%, it goes to GPUs. So it's kind of, it depends on the problem. So it's very difficult to do a load balancing at hardware level.
Thank you very much.
Yeah.
他にご質問のある方いらっしゃいますでしょうか。
Hiraki-san.
Thank you for excellent your speech. I had one question. Is software license needs for using GPU as license normal for in general?
So are you asking about a particular application? So are you talking in ANSYS or are you talking about Abaqus? So if you take an ANSYS, for example, in 15.0, as I explained, the GPUs are treated the same as a CPU core. For example, today, if you want to run your simulation on Ivy Bridge socket, it has 12 cores. So you need 12 HPC licenses. But this whole NVIDIA GPU, the whole socket only uses one HPC. So that was a very good and favorable change for GPU acceleration. Similarly, in Abaqus, you can use the same number of tokens even though you turn on GPUs. So that licensing mechanism is favorable too. So a lot of ISVs not only doing this GPU-based development, but they're also relaxing, I would say, or changing their licensing policy so that customers can leverage GPUs. So with ANSYS, for example, if you have HPC licenses, you don't need any new license. You don't even have to, upgrade any of those. So the same ANSYS HPC license that you had before will handle GPUs. You don't need anything, special there.
Thank you.
もう一つぐらいお受けしたいと思いますが、ご質問のある方いらっしゃいますでしょうか。よろしいですかね。それではご清聴ありがとうございました。Thank you.
Thank you very much.